Continuing looking at buffers and then at titration curves. Now, buffer solution, recall, consists of either a weak acid and the soluble salt of its conjugate base, or a weak base and the soluble salt of its conjugate acid. So, for example, acetic acid and sodium acetate could form a buffer. It produces a high amount of both the acid and its conjugate in solution, which allows, based on the equilibrium, any acidic component to neutralize a base, or the basic component to neutralize an acid. So any addition of strong acid will be neutralized by the acetate. Any addition of strong base will be neutralized by the acetic acid. Now the capacity of the buffer, the ability that it has to react with the strong acid and strong base solutions that are added, depend upon the concentrations of the acid and its conjugate. Buffer capacity is what we refer to when we talk about how much strong acid or strong base can be neutralized with very little change in the pH. So for a 0.01 molar amount of sodium hydroxide added to a 1 liter solution of a buffer of 0.1 molar acetic acid and sodium acetate, the pH will increase from 4.74 to 4.82. This functions as long as the necessary species exist in solution. So as long as I have either acetate or acetic acid, depending on what I need to neutralize, I can continue to resist changes to pH. Adding acid, as long as there is acetate, will resist pH change. Adding base, as long as there is acetic acid, will resist pH change. If I add HCl to the buffer, I'm going to increase H3O+. That H3O+ is going to shift to the left to produce acetic acid. But if I don't have any more acetate, I cannot make that shift. My equilibrium breaks down. Because adding acid raises H3O+. That's going to shift Q to the left, or shift Q to be the right, and it needs to move to the left until it reaches Ka again. When I completely consume the acetate, adding the HCl will raise pH much faster. Now, preparing a buffer is something of a tricky subject. We can prepare a buffer by combining an acid or a base with its soluble conjugate salt. Now, one way to do this is to combine solutions of both the salt and the acid or base. If we take, for instance, 200 milliliters of a 0.1 molar solution of sodium fluoride and 100 milliliters of a 0.05 molar solution of hydrofluoric acid, which has a Ka of 7.2 times 10 to the negative 4, we can determine the pH and the hydronium concentration in solution. Our equilibrium process is hydrofluoric acid plus water produces fluoride plus hydronium with a standard Ka expression. 0.2 liters of 0.1 molar solution is 0.02 moles of sodium fluoride. 0.1 liter of 0.05 molar solution is 0.005 moles of hydrofluoric acid. Total volume is equal for both species, so the volume component cancels out, leaving us simply with moles. We can determine the pH based upon Henderson-Hasselbalch equation. So looking for the pKa is a negative log of the Ka at 3.14. Our pH then is 3.14 plus the log of my base over my acid, 0.02 over 0.005, which gives us a pH of 3.75. The hydronium concentration is 10 to the negative pH, or 1.81 times 10 to the minus 4 molar hydronium. We can also prepare buffers by combining an acid or a base with the soluble conjugate salt in a solid form. So if I take the salt and I add it to a solution rather than adding two solutions together, I can get a much more controlled buffer. And I can create a buffer with the specific pH more effectively this way. So for example, what mass of ammonium chloride must be added to a 500 milliliter portion of a 0.1 molar ammonia solution to generate a buffer of 500 milliliters with a pH of 9.15, given the Kb at 1.8 times 10 to the negative 5. Our POH is equal to our pKb plus our log of our ammonium over ammonia. 0.5 liters times 0.1 molar gives us 0.05 moles of ammonia. Our POH is the 14 minus the pH of 9.15, or 4.85. So 4.85 equals 4.74 plus the log of ammonium to ammonia. If I move the pKb over to the left to isolate the log of ammonium over ammonia, we get 4.85 minus 4.74, which equals 0.110. So 0.110 equals the log of the ammonium over the ammonia. We can cancel the log by taking 10 to the log, so 10 to the 0.110 equals the ammonium to ammonia ratio.
10 to the 0.110 is 1.288, which equals our amount of ammonia we need divided by the amount of ammonium we need divided by the amount of ammonia that we have. We just calculated earlier that we have 0.05 moles of ammonia. So we have 1.288 times the 0.05 moles of ammonia gives us a needed amount of 6.44 times 10 to the negative 2 moles of ammonium chloride, or 0.0644. If we take our 0.0644 moles, multiply it by the molar mass at 53.5 grams per mole, we wind up at 3.45 grams needed in order to make this buffer at this amount and the pH of 9.15. Another way to create a buffer is to partially neutralize either a weak acid or a weak base solution. We can take that solution, partially neutralize it with either an acid or base, depending on what we have, and we can get a buffer solution from that. So for example, what pH buffer will reacting 50 milliliters of a 0.6 molar solution of sodium hydroxide with 100 milliliters of a 0.8 molar acetic acid solution form? So far we've worked in liters and molar. We can also work in milliliters and millimolar. Now remember, if we're doing this, then the concentration of our millimolar and molar will be equal in magnitude. So if I have a 0.1 molar solution, that would be a 0.1 millimolar solution. So taking 50 milliliters times 0.6 millimolar gives us 30 millimoles of sodium hydroxide. 100 milliliters times 0.8 millimolar gives us 80 millimoles of acetic acid. 80 minus 30, so reacting 30 of the 80 acetic acid gives us a total of 50 millimoles of acetic acid left, and it generates 30 millimoles of acetate. To find the pH, we have pH equals pKa plus the log of the conjugate base of the acid. So pH is 4.74 plus the log of 30 over 50, or a pH of 4.52. Combining different acids and bases together will produce more complex and specific buffers to get even more targeted pHs. However, they're generally harder to calculate in pH. Now, a titration curve is a special curve or graph that we can create that plots a titration process. Now, titration involves adding a known invariable reaction. So we have something, for instance, an acid-base reaction where I know that adding the acid and the base will produce the neutralization process every time. I add a known concentration of one species, which we call a titrant, to another species that's called a titrand. So I have some sample of the titrand, and I'm adding a known concentration of the titrant to the titrand. I track the volume of the titrant that I add, and I can determine, based upon my dilution formula of the M1V1 equals M2V2, how many moles of the reactant are added at any time and how much has been neutralized. We can monitor this process to see how long it takes or how far it goes till it's complete. For acids and bases, this process is generally monitored either by an indicator or a pH meter. From our titration data, we can plot a curve of the change in the titrand solution with the addition of the titrant. For an acid-base reaction, there are three different types of curves we can get. We can get a strong acid, strong base curve, a strong acid, weak base, or a strong base, weak acid curve, or a weak acid, weak base curve. For acid-base reactions, the solution pH will depend on the concentration of every species at any particular time. Indicators used with acids and bases are generally organic molecules that respond to changes in the solution. And most of these indicators will have a useful pH range. That's the range over which they give a physical response or physical change. Acid-base indicators generally change form depending on whether they are protonated or deprotonated. So if I have IN as a generic indicator, HIN is a protonated indicator, IN minus is a deprotonated indicator. We have an equilibrium between the protonated and deprotonated forms. A basic solution will get rid of a lot of the hydronium on the right. Removing the hydronium on the right will shift the equilibrium towards the right, creating the deprotonated form of the indicator. If I'm in an acidic solution, I will have a lot of hydronium, and I will shift towards the left. So looking at a strong acid, strong base titration curve, equilibrium doesn't apply in this sense because all species ionize completely. We can measure pH as volume is added and plot a curve from that. We can also predict what pH we would expect based upon certain amounts of a solution added, calculating concentration changes. Once the concentration of the acid and the base are equal,
when I have a complete neutralization process, I reach what's called the equivalence point. Now for a strong acid, strong base, this will generally be at a pH of 7 because there's no buffering going on. The indicator will generally change color near this if I'm using a proper indicator, and the point at which the indicator begins to change is called the endpoint. Now it's not always exactly at the equivalence point, but it will generally be around it. So if I take 100 milliliters of 0.1 molar hydrochloric acid and titrate it with 0.1 molar sodium hydroxide, if phenolphthalein is an indicator, which has an effective range of 8.5 to 10, I can calculate concentration versus pH such that if I start off with no sodium hydroxide added, the hydronium concentration is still 0.1 molar, which gives me a pH of 1. The 100 milliliters of my 0.1 molar acid contain a total of 10 millimoles of acid. If I add 20 milliliters of base, I will have added 2 millimoles of the base. So after 20 millimeters, my amount of acid that remains is 8 millimoles, so because 10 minus 2 is 8. The total volume of the solution is the 100 milliliters of the acid and the 20 milliliters of the base at 120. 8 divided by 120 is a molarity of 0.067, and the negative log of that is 1.17. I can calculate these pH versus volume changes and tabulate a series of changes. So for instance, 0 sodium hydroxide gives us a pH of 1, 20 gives us 1.17, 50 gives us 1.48, 90 gives us 2.28, 100, which is the equivalence point, gives us a pH of 7, neutral. If I go and add 110, now I'm working in base. I now have 1 millimole of base in the solution, and I have a pH of 11.68. Taking these data points, I can plot a curve that looks at the change in pH versus volume of the solution. So this curve is relatively very, very low slope until it nears the equivalence point. At that point, it begins to shoot up very rapidly and then level off again. We see that the indicator has only an effective range from 8.5 to 10. However, because the slope of the curve is almost straight up at that point, the amount of change in volume that occurs going from the pH of say 8 to pH of 10 is very, very small, which means that the error in our equivalence point versus our endpoint is also very small. For weak acid and a strong base titration, as an example, the equilibrium process occurs, and it will buffer before the equivalence point. I can measure pH as volume is added once again and plot a curve, and predict the pH of the solution by calculating the concentrations. So for an analogous situation with 100 milliliters of 0.1 molar weak acid in the same phenolphthalein, at 0, our pH is 2.78. And if you remember from the ICE calculations we did earlier, we knew that a 0.1 molar acetic acid solution has a 2.78 pH. If I add 20 milliliters of base, my 100 milliliters of acid at 0.1 molar contain 10 millimoles of acid. Adding 20 milliliters of base adds 2 millimoles of the base, which means that I've used up 2 millimoles of the acid. I have 8 left. I've also formed 2 millimoles of my conjugate. Because this is a weak acid, we have to use the Henderson-Hasselbalch equation to calculate pH. So pH is equal to pKa at 4.74 plus the log of 2 versus 8, which gives us a pH of 4.14. So we went from 2.78 to 4.14. We can tabulate a series of values. At 0, it's 2.78. At 20, it's 4.14. At 50, it's 4.74. At 90, it's 5.70. At 100, it's 8.72. At 110, 11.68. And we can plot a titration curve for this as well. You see that it goes up slightly, and then it begins to level off. The region where it's leveled off from about 4 to 5 pH range is the buffering region for this. As we start to near the equivalence point at 100, it shoots up again. These two titration curves that we've seen would be reversed if it was titrating a base with an acid. They would just start at a high pH and go to a low pH. Now we can also get weak acid, weak base curves, but these are very difficult because it buffers both before and after the equivalence point. So generally, these are very hard to calculate.